So we are continuing with 4.1. So this is, I'll say 4.1 continued. Today we're going to talk about graphs of exponential functions, and that's going to help us get a better feel for what these functions, literally what they look like, because that's what a graph tells us, is what a function actually looks like. So we're going to talk about graphs of two particular classes of exponential functions. So I'll say we want to consider the graphs of exponential functions which, remember, we're of the form f of x equals a raised to the x. So the variable is in the exponent position. That's the thing that is varying. As the input changes, that exponent is changing and the base is staying the same. So we want to consider the graphs of exponential functions like this in two categories. The first one being where a is greater than 1. So we already know, if you recall from the definition, that a cannot be equal to 1. Well, it can be, but then it won't be an exponential function because you'll just have a bunch of 1s. It'll just be a constant 1 function. We're going to consider this in two categories. We know that we want a to be greater than 0, but not 1. So we're going to consider the case where a is greater than 1. And then we're going to consider the case where a is between 0 and 1, like fractions. Specifically, fractions less than 1. Fractions can be greater than 1, right? So let me say fractions less than 1, like 1/2, 1/3, 2/3, 1/4, etc. So we're going to consider them in these two categories. Okay. Okay, so why are we doing this? Why are we considering them in these two categories? Well, at this jump over the number 1, like where the base turns from a number smaller than 1 to a number bigger than 1, there's a drastic difference in the graphs. So that's kind of that's why we split them into these two categories when we're investigating them. So what do I want to do? I want to draw graphs of, I'll do a couple examples drawing one graph in this category and then one graph in this category, and then we'll probably go to Desmos to be able to look at a broader range of functions in each category. I want you to see how you do it by hand for at least one of each, though. Okay, so let's call this example 1 for today. And let's say split these into two examples. So let's sketch a graph of f of x equals 3 to the x. All right, so what do we fall back on? What do we fall back on whenever we don't know how to draw a graph of a function? It's a new type of function, right? What do we fall back on? A table of values, right? And you may recall that there are typically good choices to make for the table of values, and that experience, kind of knowing what the function is going to do. And of course, that's going to come from me. I'm going to help you pick the like a efficient choice of input values to pick for our table of values. Now, in this case, I think it's going to be just fine to pick sort of the classic 5 values, -2 to 2, for our inputs x. And then our outputs on this side will be f of x. 3 raised to the second power, I'm starting at the bottom because these are easier to deal with, right? So 3 raised to the second power is going to be 3 squared, which is 9. Okay, so that's coming from 3 squared equals 9. 3 raised to the first power, 3 raised to the first power is just 3, so that'll be a 3 there. 3 raised to the 0th power is 1. Anything raised to the 0 power is 1. So you may want to write that down maybe parenthetically right here if that's not a fact that you know or forgot. Maybe write down anything raised to the 0 is equal to 1. That's how I'll write it there, where A represents any number. Maybe you'll want to write it in words though. Now, so I got that. That's 1. Now, what about 3 raised to the -1? What about 3 raised to the? So now we need to recall our exponent rules. Exponent rules tell us 3 raised to the -1 is the same as 1 over 3 to the first power. That's a 1. 1 over 3 to the first power. That's what a negative on the exponent does. So that's just 1/3. So I got to squeeze that in here. That's 1/3. Then 3 raised to the -2nd power is the same as 1 over 3 squared. That's going to be 1 over 9 because 3 squared is 9. So let me explicitly write out these coordinate values that we just got. We got -2, 1 over 9. So that's a very small y value at this x value of -2. We got -1, 1/3. Another fractional value. We got 0, 1, we got 1, 3, and we got 2, 9. Those are our 5 points that we just got from making our table of values. The important thing, I would say the critical thing is understanding what the negative exponent does, right? It just flips, it's a reciprocal. That's what the negative exponent does. Okay. So now we would graph these 5 points. If we're trying to sketch a graph, that's what we do. We find points via a table of values, and then we graph the points. Because we don't have any techniques right now for graphing these things other than just making a table of values. If it was a quadratic or polynomial function, we have a bunch of techniques for that now. Why is my going on? Okay, so we have a bunch of techniques for other kinds of functions, but not for these exponential functions because we're still investigating them, right? So I know my x-axis only ranges from -2 to 2, so maybe I can just kind of say 1, 2, I'll just go out to 3 in each direction on x. My y values go all the way out to 9. They go from very small, 1/9, that's going to be hard to graph, right? All the way out to 9. So maybe I'll say 1, 2, 3, 4, 5, 6. Hopefully there's enough room. Yeah, there's 9. So I barely left enough room for that y-axis there, or for that coordinate point. In fact, I'll start with that one. That's 2, 9. So at x equals 2, I'm all the way up at 9. The next coordinate point is 1, 3. So at 1, I'm at 3. 0, 1 is the next one right there. So far, those are relatively easy to graph. They're all whole numbers. Just got to remember how points graph, right? The next one, x value is -1, so somewhere around here. It's at y equals 1/3, so I'll just kind of put it there. Y value of 0.33, so somewhere around there. And then the next x value at -2 has an output of 1/9, which is 0.111, etc. Which now we're getting into like, how do I really graph that? I'm just going to like plop it right on top, not on the x-axis, but right above it, like right there. Anything smaller than this, it's just like to go further into the negatives would not really be useful here, right? For a hand-drawn graph. And in fact, honestly, going any further this way wouldn't be that useful either, because think about what the next coordinate point would be. At x equals 3, remember the function is f of x equals 3 to the x. So at x equals 3, I would have a y value of 27, which is like way up there, right? So really, graphing these 5 points is really, I think, like the is just fine for getting a sketch. So we follow the shape of the graph here, and we're getting that nice exponential shape. It's going off to infinity very quickly, right? Because at 3, it's going to be all the way up at 27, so it's growing very quickly. And over here, it's tending towards this x-axis, but recall we looked at this last time that it will never cross. It will never actually touch the x-axis. It just gets very, very close. So here's a nice exponential graph by hand. I'm going to talk about a few things here. I want to say something about asymptotes. Recall when we were graphing like the 1 over x functions, 1 over x squared, 1 over x, 1 over x cubed, they had sort of shapes like this, but there would be like one L shape in the first quadrant and then another one down here maybe. They had both horizontal and vertical asymptotes. Now, since this graph kind of looks similar, I want to point some things out about it. Just be clear about what's happening with the asymptotes here. First, I want to say there are no vertical asymptotes. Like, it may look like it's approaching some vertical line here, like it's going to just like start hugging some vertical line because it's growing so fast, but it really doesn't. It keeps growing this way and that way. It's just growing taller way faster than it's growing horizontally, but there are no vertical asymptotes. Even though it kind of looks like it might be approaching like a vertical line, it doesn't. It keeps growing both that way and that way. There are, or let's say there is a horizontal asymptote though. That's what's happening when this thing is trying to touch trying to touch the x-axis. There is a horizontal asymptote at the not the y-axis, at the at the x-axis. And by the way, this is where y is equal to 0. So you notice if I keep plugging in higher negative values, the fraction is going to keep getting smaller and smaller. The output value, the y value, keeps getting smaller and smaller and smaller, but it will never actually touch the x-axis. That is a horizontal asymptote. So we would say there is a horizontal asymptote right here, which I guess I could draw as a dotted line, but it is the x-axis. I'm pointing that out because that will be helpful when we look at transformations of these graphs, just like it was helpful for transformations of those 1 over x squared graphs to look at their asymptotes and where their asymptotes are moving if you scoot the graph around. The same thing here. If we try to scoot this graph up or down, knowing where its asymptote is moving is going to be very helpful because its asymptote is going to move with the graph. And that's going to be a helpful thing to point out if we're trying to graph these, when we're graphing transformations of functions like this. So I said that I was going to do one of each category by hand. So this is the first one in the category of A being greater than 1. See, A is the 3 here, right? The base. So I've done one of these. And now I'm going to do one of these where A is between 0 and 1. Okay. So example 2. We'll say sketch a graph, and I'm going to pick a sort of symmetric example. I'll say g of x equals 1 over 3 to the x. 1 over 3 to the x. Okay, so make a table of values. So 1 over 3 is the a. It's between 0 and 1, right? It's less than 1. All right. Make it a little bit bigger here, and then g of x here. Same values, -2, -1, 0, 1, and 2. All right, let's consider these. G of x equals, okay, so we'll start with the positive value again. So we'll say g of, g of 2 is equal to 1 over 3 raised to the 2, which is the same as 1 squared over 3 squared, which is the same as 1 over 9. Okay, so that's all that happens there. Plugging in 2, you're just squaring the top and bottom. Of course, squaring the top, 1 squared is just 1. So really, it's just you're squaring the bottom number because the 1 doesn't really change, right, when you square it. So 1 over 9. Okay, so we're getting our fractions at the positive values this time. Let's see if that continues. G of 1 is equal to 1 over 3 to the first power, but that's just going to be 1 over 3, right? That's just 1 over 3. So this one here is 1 over 3. Now, G of 0, so I'm working my way up the table of values here. G of 0 is 1 over 3 raised to the 0, but we already know by definition that that should be 1 because anything raised to the 0 is 1. So that gives me my first whole number, 1. G of -1, now this is where it gets a little interesting. That's 1/3 raised to the -1, but I know the negative exponent means I should flip that fraction, right? Take the reciprocal. But what's the reciprocal of 1/3? It's 3 over 1, right? So technically this is the same as 3 over 1 raised to the first. See how the negative is used up? The negative gets used up by flipping the fraction. And then of course, this is a whole lot of stuff going on here just to say 3, right? Because 3 over 1 is 3 raised to the first power is 3. So that one is 3. Similarly, G of -2 is 1 over 3 raised to the -2, which is, so I'm going to use up the negative to flip this, 3 over 1 squared, which is just a fancy way to say 9, right? 3 over 1 is 3, and then squaring it gives me 9. So it's no coincidence at all that we're seeing like a symmetry with example 1. Basically, all these output values are flipped around. Yeah, they're just flipped around. And why is that? Well, let's sketch the graph, and then I will answer that question. Okay. I'm going to graph these 5 points, At -2, I'm all the way up at 9, which is the highest tick mark I graphed here. So at -2, I'm all the way up at 9. Did I say -9? I meant +9. +9, right? That's this value here. -1 is at 3. We go through 0, 1 again. Oops, dang it, 0, 1, which is right here, not there. And then we go through 1, 1/3. So at an x value of 1, I'm at 1/3, roughly there. And then at an x value of 2, I'm at 1/9. So again, it's getting tough to graph those values that are getting very small. So I'm going like this. And it should be squeezing close to the x-axis, getting closer and closer to the x-axis and exploding off to infinity that way. Again, there is a, let me scoot this up, like this. Again, there is a horizontal asymptote at the x-axis at a y value of 0. It's never going to output a value of 0. It tries to get very close, but it never will. And there is no vertical asymptote. All right, so if I was to plop these graphs on top of each other, let's compare graphs and see if we can figure out what is going on, why they look so similar in their table of values. Well, if I was to just quickly do that, 1, 2, 3, 1, 2, 3. So the first one I'll draw in blue. That was the 3 to the x, and I'll just very quickly graph it, a sketch of it. Here's the first one we did. So this is the 3 to the x. And then the second one, which I'll do in green, was 1 over 3 to the x. Let's see, so all the way up here at -2 and right here. Very nice symmetry happening here. So this is 1 over 3 to the x. So what's going on here? What we can do is we can say, oh, these are, what's the relationship graphically? These are reflections of each other over the y-axis, right? If I take either one of these and I spin it around the y-axis, then I get the other function. If I take this green function and flip it over the y-axis, then I'll get the blue function. So these are reflections of each other over the y-axis. And does anyone remember what we have to do to the function, to a function, to make it reflect over the y-axis? So remember that if we negating the x, we had all those rules from chapter 2, like section 2.6, where if you negate the whole function, then it flips over the x-axis. And if you negate just the input, the x value, then that results in a flip or reflection over the y-axis. So can I still, what's the point? What am I getting at here? Well, if negating the x results in a flip over the y-axis, consider, do it in a different color here. Take that 3 to the x function, make its exponent negative, but that's the same as using up the negative. That's the same as flipping the 3 to make it 1 over 3 to the x. And also I could say 1 over 3, make its input negative, and that's going to be the same as 3 to the x. So they are very much related to each other. In fact, the way that they're related is they are reflections of each other over the y-axis, and we kind of prove it here using the tools from chapter 2 and exponent rules, right? Okay. Okay. What's next? Oh, now I'm going to go to Desmos. Get my mouse here because it's hard to do on the notepad thingy. Let's see. You guys don't want to look at my homework. Desmos, let's look at some other exponential functions. So we just graphed 3 raised to the x. There's that one. Let's look at 2 raised to the x and see how it compares. So we see the 3 raised to the x function grows faster. That's the red function. It grows faster because that base is higher. This is like a tripling function. Every time you input a new whole number, it triples. Is that a good way to say that? Yeah. And the blue function is like a doubling function. Like every time you input the next whole number, it doubles the output. So clearly this one is growing faster. So then if I plugged in like 4 raised to the x, it'll grow even faster. 4 raised to the x is there, that green function. And then 5 raised to the x is there. So the higher the base, the faster the function is going to grow. And just in case you're curious, what does the 1 to the x function look like? Why don't we consider that? Well, there it is. 1 to the x, right? We're not allowed to consider that as an exponential function because look at how it grows. In fact, it doesn't grow. It's constant. So this is not an exponential function, so we do not consider that. And we also do not consider negatives. What happens if I force a negative into the base? Yeah, Desmos doesn't even want to graph it. They should graph something. That's weird. It bounces around for every. Well, yeah, I guess that would be hard to graph. It bounces around for every positive, even and odd x value. So what is that? What does even and odd even mean when you're talking about like irrational numbers, right? So I could graph it for you for 0 to 10. Let's let the step be 1. Integers. But it's not even going to do that. Well, whatever. You see, it breaks when you try to give it a negative base. So let's look at some fractional ones. Let's say 1 over 2. Yeah. X. Okay, there we go. That's nice. That's nice. It's symmetric to this, or yes, symmetric around the y-axis to this 2 to the x function. And then we could do one over 3 raised to the x. And it's going to be symmetric to this 3 to the x. In fact, those are the two that I just graphed by hand. And I think you get the picture. 1 over 4 to the x. Whoops. And let me go ahead and graph 1 over 5 to the x, and let me make their colors line up just for convenience. There we go. Very nice little picture here showing how these things are symmetric. Now, every single one of these, all 10 of these that I graphed, all go through that point, 0, 1, because all of these, when you raise it to the 0th power, you get an output of 1. So every single one of them meets right there at 0, 1. That's a nice picture. Okay. All right, so what else can I say? Notice that all of their domains are the entire real line. There's no problem plugging in any number you want into the function, into the x value for all of these. Also, all of their ranges are from 0, not including 0, but from 0 all the way up to infinity, right? They never go into the negatives. So their ranges are from 0 to infinity, which I pointed out last time. Okay. Let's do a little quick example here, just to make sure we understand what's going on with these graphs. We can do a lot of modeling too with exponential functions, which I think I talked about last time. So we will try to get to that today, looking at compound interest in particular. Okay, but first, let's just do a little bit more practice with these exponential functions. So let's say I said find the exponential function, in other words, find that letter a, whose graph is given. So let's say I give you like this function and I say it goes through, let's say I'm going to say that this is so the y-axis is counting in increments of 5, just for the sake of being able to graph this, and then the x-axis is counting in increments of 1. And let's say that it goes through 0, 1 as usual, and then it also goes through 2, 25. Knowing that it goes through 0, 1 is not helpful because they all go through 0, 1, but knowing that it goes through 2, 25 is helpful. So how can I find, I'm trying to find what this exponential function is. In other words, I want to be able to write down like f of x equals something raised to the x. So how can I figure that out? Well, if I know the input at 2 is 25, then what I know is that f of 2 is equal to 25. That's the same as saying, well, a raised to the 2, right, input of 2, I don't know a, is equal to 25, an output of 25. Okay, so that tells me that a must be 5. Right, a must be 5. So f of x equals, oh, dang it, 5 raised to the x. F of x equals 5 raised to the x. So that just comes from pulling this point and plugging it in right here. X is 2, the output is 25, and then just solving for a. By square rooting, right? I mean, or you could just say, oh, what squared is 25? Probably easier to just ask it that way, but technically you can take a square root on both sides and you'll get a equals plus or minus 5, but you know minus, you can't have that minus going on here. It has to be the positive version because of the way we define our exponential functions, so it must be 5. Right, what about b? So this time we have a graph. Okay, sorry, just looking at the example. So 1, 2, 3, and -1, -2, -3, and then sometimes in the graphs in the book and in example problems, the y-axis will be squished or it'll count in a larger scale for these exponential functions just because they grow so fast. And if we draw them with the same scale, like on the x and y axis, just counting by ones at the same scale, then that really limits what you can draw by hand or draw a picture of. Because, you know, I couldn't draw this 5 to the x function and graph this point 2, 25 if I made each of these increments just 1, right? My graph would be too big. All right, so now this one, they tell me goes through 0, 1, which is normal, and it also goes through this point 3, 1/8. Let me turn my paper for a moment so I can graph this function. And I'll just kind of draw it like that, not worrying too much about this side, worrying more about that point that they explicitly gave me there. So I'm going to have okay. So I'm going to have a raised to the 3rd power. Right, that's the input. A raised to the 3rd power should give me an output of 1/8. So maybe that's a little bit trickier. What cubed is equal to 1/8? Well, I can maybe solve this by saying I know I can take a cube root on both sides. Okay, and then that is the same as a is equal to the cube root. I can split the root, right? Just like all that time ago, that long time ago, we were talking about these sort of rules for radicals. I can split it up, and then a is going to be 1, right? Cube root of 1 is 1. 1 is a nicely behaved number. You cube it, cube root it, it doesn't change, right? Cube root of 8, what times itself 3 times is equal to 8? You think about that for a minute, you'll figure out that it's 2. So that means my function has base 1/2. So this is that function, which looks right? If it's angled like this, where it's growing to infinity on the negative side, then it should be one of those fractional functions, or with a fractional base is what I mean. Fractional base less than 1, like this. Okay. I really want to get to the compound interest stuff. The next thing, like on the agenda, is transformations of these functions, but let me check something real quick. Actually, no, I already know that we don't need to emphasize that too much. So I'm going to skip that transformations of exponential functions for now. Maybe I'll come back to it later, but I really want to get to the compound interest stuff. So we're changing gears here a little bit, not investigating these exponential functions just for the fun of it anymore. We're actually going to look at an exponential function that is used in real life every day by anyone who cares anything about a savings account or just anything that bears interest. Okay, so compound interest. So compound interest is going to be can be modeled by an exponential function. It's going to look quite different from the exponential functions we were just dealing with, but I'll explain. Can be modeled by an exponential function whose base is dependent on certain parameters, certain given parameters. Those parameters being the principal, which is the initial amount of money, So I'm telling you what the base, remember base is that letter A, the A to the X, the lowercase a raised to the X. That lowercase a is what we call the base of the exponential function. The base of this compound interest function is going to look way more complicated. There's a lot more going on, but I'm just kind of building up to that. So the initial amount of money is one thing that it will depend on. It's also going to depend on the rate of interest. Oh, let me tell you what we denote these by. We denote the principal by a capital P. We denote the rate of interest by an R. The rate of interest is a percentage that you're given by your bank. And N, oh, sorry, I'll tell you what it is first and then tell you what the letter is. It's also dependent on the number of times interest compounds per year. We denote that by the lowercase letter n. all of this is going to have a bearing on what the base of our exponential function is, which, if you think about it, makes sense. If you know, just you kind of have an intuitive idea of how like your savings account might work if you are lucky enough to have a savings account, right? That, you know, if there's the amount of money that is growing in there depends not only on your rate of interest, but it also depends on how much money is in there, right? If you've only got 50 bucks in there, it's not going to incur a lot of interest. If you've got 5,000 bucks in there, then it's going to incur more interest because the interest is based off of that principal. Also, it's going to depend on how many times your bank compounds your interest, which means, like, do they calculate your interest only once per year, or do they do it 12 times per year? Do they do it monthly? You know, because so we'll investigate that. There's a lot to say about that. So the base of this exponential function is going to depend on all of these things. Also, I want to say we use t, the letter t, as our input variable instead of x. In this case, we've been using x, right, because x is like the go-to for generic functions, but here we're going to switch to t as our input variable because input is now, it measures time, specifically in years. So t for time. Last thing, I got to tell you the letter that we use for the output. We use capital A. Or A specifically, I should say A. Instead of f of x, it's capital A of t as our output. So this is going to be the amount of money in, like, you can think of it as a amount, capital A for amount, as our output. Okay. So here are all the pieces. Here are all the pieces. This is going to be the amount in your account after some number of years. And all of these things are going to be involved in the formula as well in the base. So let me just go ahead and write down the formula now. You may have seen this before. It's a pretty popular formula. A of t is equal to the principal, so the principal is getting involved here, times, and then 1 plus r over n, close parentheses. So there's the p, r, and n, and get p, r, and n getting involved in the base, right? T is not involved yet, so this is still just like some constant here. And then this part is raised to the n times t. So finally, there's our input variable coming in, and there is an n attached to it up here. So that's not, that n is not technically in the base, right? But it's attached up there next to the t, but that's fine. That's fine. So there it is. There's the formula for compound interest given some principal amount starting off in the account, given some rate of interest that would be given as well, and some number of times that the account compounds interest per year. So let's do an example. I believe this is example 4 for today. I'm going to use this formula. Let's say a sum of $1,000 is invested. Find the amount in the account after 3 years Okay. So how does this apply to real life? Well, I mean, maybe we don't have money to invest right now in a savings account, at least maybe not that much, but in the future, or maybe like you got your, your STEMI check in and you decided to save it, and your bank tells you this is their interest rate and they compound semi-annually. You want to see how much money am I going to have in 3 years based off of this $1,000 that I put into this savings account. Maybe you're thinking about switching banks because another bank tells you they give you 10% interest, but they compound monthly. So maybe that would be a good question. You'd want to calculate each to see who's going to give you more money. So let's do this one first, though. So here's how it goes. First, we want to plug, first we want to figure out what each of these numbers is. So P is going to be that initial amount. I'll drop the $sign, right? Just worried about the number. R is going to be 12%, but anytime I'm using percents in math, when I put them on paper to plug into a formula, always got to convert them to decimals. Okay, so there's R, 0.12. N is going to come from how many times it compounds per year. Semi-annually means twice a year. You just kind of got to know that. So annually means once a year. Semi-annually means twice a year. Quarterly means 4 times a year. Monthly, 12 times a year. Daily, 365 times a year. There's a table on page 371 that says all of that I just said in case you missed it or aren't sure about one of them. You can look at that table. So for us, though, semi-annually means compounded twice per year. By the way, T, specifically for what we want, T is 3. 3 years. So we're going to say A of 3 is equal to 1,000 times 1 plus 0.12 over 2 raised to the, raised to the 2, right, that's N, times 3. There's the T value, 3. Notice how the T is, I've plugged it in as the input here, represented it in this little window in the function. Okay, how do you actually calculate this? Let me show you with my calculator. You're going to want to be careful here. Make sure that you're wrapping things in parentheses as needed. So I will say, trying to make sure. Okay, I think if I hold it like this, that's fine. So I'm going to say 1,000 and then times, so I'm opening parentheses and I'm going to say 1 plus 0.12 divided by 2, close parentheses. So that's this part. And then raised to, now got to wrap this exponent in parentheses, 2 times 3, and then close that. Or you could just say like raised to 6, right? If you know what this little n times t part is, like if it's just 2 times 3, then you could just say raised to the 6. But if you want to completely plug it in, without worrying about doing that multiplication, make sure you wrap that exponent in parentheses, because otherwise your calculator will just raise everything to the 2 and then take that and multiply it by 3 instead of raising the whole thing to a 2 times 3. So there it is. I'm getting, of course, it's a dollar amount, so I'm going to want to round to, come on. Pencil there, marker. I'm going to say, I'm going to round to the 100th place. So 1418.52. So after 3 years, we will have $1,418.52. Now, I had mentioned, what if you're comparing another bank's interest rate for the same principal, the same amount of money, same time span? Let's compare, as an extra problem here, let's compare that earns 10% interest, which is lower, right? So maybe you're thinking not as good, but compounds more often. Let's say monthly. Okay, so the principal and the time are the same, but R is now going to be 0.10. So P is still 1,000. R is 10%, which is 0.10, or just 0.1. N is 12 because compounds monthly, and T is still 3. A of 3 then is going to be 1,000 times 1 plus 0.10, that's R, over N, which is 12, raised to the 12, that's N, right, times 3, NT, 12 times 3. So I will, I lost my calculator. Here it is. So I'll say 1,000 times 1 plus 0.10 divided by 12. That's the inside there. Raised to, and then open parentheses, 12 times 3, close parentheses, equals, let it think for a minute, and then we have 1348.12. All right. So clearly your current account, or account 1, with the higher interest rate and lower number of compoundings, earns more money. So there's a lot more to say about this number of compoundings thing. For instance, let me just explain what this compounding thing is. If they compound twice a year here, that means at one point in the middle of the year, they take your $1,000 and they stack interest onto it. Okay. Then they do it again at the end of the year, but now your new principal is not $1,000 anymore. It's whatever the interest was that got stacked on. So that's what compounding does. It takes, like, here's your sum of money, and then they say, here's a little bit more interest. So now your sum of money grows a little bit. And then the next time they calculate interest, it's on this new bigger part, right? This bigger sum. So the little part they pull off as interest and then give back, or the part that is interest that's given back to you is slightly bigger. So you would think that the number of compoundings matters very much. And in fact, you would think that if you had an account that was compounding every second of every minute of every hour of every day, then you would potentially have infinite money, right? But we'll look at in the next section that you actually don't reach this infinite amount of money. You actually reach a base for your exponential function that is a very nice, clean number, and that'll be what we investigate in 4.2, which is called the natural exponential function. Okay, so if there are no questions, we have a few minutes if you guys have any questions about any of this or any WebAssign questions. But if not, you guys are free to go for today.